let's talk about the mean. So let's find the mean of these data. Before we do that, let's talk a little bit about what the mean is. Let's say that we have a number line, and our data begin at 3 and end at 8. And let's just take each individual value and just set them on the number line where they belong. So we start with a 5, and we have a 4 and an 8, 2 6s, so we'll stack those up, and a 4 and 3 5s and a 3. Okay. So what we've done when we stack all these up is we see that we have a nice symmetrical slope here, where we have a clear peak in the middle, and then a nice descending ski slope to the left, and a nice descending ski slope to the right. And since this is symmetrical, well, it needs to be symmetrical, and when it is, we call it a normal bell curve, or sometimes just a normal curve. And what we're trying to do with the calculating the mean is just find, well, what we're really trying to do is where is this peak. But we're going to do it by finding where is the balance point on our number line that would if our number line were a teeter-totter, that would keep it perfectly flat. And so the goal is we'll have just as much weight over here on the upward side of the number line as we do down here on the downward side of the number line. And so if we had, for example, if we added a 12 to this data set, clear over here on the right, that would increase weight over here on the right side. And so in order to keep the number line flat, we would have to move our fulcrum to the right in order to account for that, right? So we're trying to keep it all completely balanced. So all we're looking for is this point that balances our number line, so we have just as much weight on this side as we do on this side, right? So let me erase this and give us a little room to do the math, but I'll show you how that works. We're trying to find the point that has just as much weight on the left as we do on the right. So if we subtracted everything below the mean from everything above the mean, it should be 0. So some people define the mean actually as the point where if you subtract the mean from each observation and then sum it up, the answer will be 0. Which the only way that can happen is if there is just as much observations below the mean as there are above the mean. That would make that come out to 0. The way we calculate the mean, though, is we're looking for the mean of x, and to indicate mean, we just put the bar above the top. So that means we have the mean of x, and that is equal to the Greek letters capital sigma, which we use to indicate summation or adding, divided by our n. So over here in our data set, we have this first 5 is x sub 1, or the first x value. The 4 is x sub 2, or the second x value. The 8 is x sub 3, or the third, on and on and on until we get to x sub, in our case, 10, but that's also x sub n because we have 10 observations in this case, an n of 10. So the sigma, all that means is we're going to start with I equal to 1, which in this case would be our 5. And we're going to add it to then when I is equal to 2, which is the 4, and add that to when I is equal to 3, which is the 8, and we keep going until we get to I equal to n, which in this case is the 3. And if we have run out of room here, but if we do that math, that adds up to 51. We already know that our n here is 10. We have 10 observations. And so in this case, our mean is equal to 5.1. Although, since our original data only go to one integer, there are no decimal places, our mean cannot be more accurate than our original data. And so we would say that we have a mean of 5. Okay, so that's how you do the math. But what you're really looking for is that balance point on a number line teeter-totter. All right, let's use R to calculate a mean. So I'll open up R, and I will open up my separate scripting window. And since I have just a short data set, I will type that in manually. My data set is going to be called x, and it is equal to the set of numbers 5, 4, 8, 6, 6, 4, 5, 5, 5, and 3. Okay. The command for mean is very, very simple. It's just, I could build it in sections. I could sum up x and then divide it by the length of x, right? The sum is the numerator, and the length gives me the number of observations in my data set, so that would be one way of calculating the mean. But there is also just a command, mean, that does all that for me. So I will highlight those and use command return on a Mac or control R on a Windows machine, and you can see that I have calculated, or I have input the data. Here I've calculated the mean using these two functions, sum and length, and here is the function using just the mean. The only thing to note here is that since these data are integer data, our mean cannot be more precise than the data upon which it was calculated or from which it was calculated. So our mean here is actually 5 and 5. Right? Because we can, let's look at another example. I have here on my desktop a comma-separated value file, which is just a list of numbers. We can see that I have just called it x. So I have just one variable here called x, and I have 2 decimal places. I just created this data set using a random number generator. But let's take a look at how I would calculate the mean for these data. So I'm just going to call this the data, and I'm going to set it equal to the result of the read.csv command for opening comma-separated value files, and I know that the data is located on my desktop and that it was called sample_1.csv. Okay. Now this is a data set, and in it I have a single variable. So if I want to remember what the name of that variable is, I can say names the data and send that over, and it tells me that the data set is named x. So to calculate the mean, I can't just say mean the data, because that's just, I need to be specific about which variable inside my data set I need to use here, and I specify that by saying $x. Okay, so if I run that line, it tells me that my mean is 9.25. Okay, so the only difference is here is that I had to use the $x to specify that I want to calculate the mean of the variable x, which is stored in my data set, the data. Okay. Another example of how we can use it to calculate the mean, and this one's simple but I think useful. We're going to use the sample data set trees. So I will open that up. This is small, so we can take a look at it. But it's just 3 variables: height, girth, and volume, and 31 observations. Each one of these are numeric. Height doesn't have any decimal places. Girth and volume have 2 decimal places. So now I could say mean trees girth, and I would calculate the mean of girth. But if I wanted to calculate the mean for all of them, I could say lapply trees mean. So lapply means apply the function mean to every variable in my list, where the list is trees, right? So instead of, this is going to calculate the mean 3 times, once for each variable. So when I run that, you can see that it has spit out the 3 means, right? So my girth was 13.2, my height was 76, and my volume was 30.2. So 3 different ways there to use the mean function, but it's pretty straightforward and easy to do.